In the name of Almighty God, I am Master Sankoshi, and today I want to talk about monolith kinetics. Monolith kinetics refers to the study of reaction rates in monolithic reactors, which are ceramic structures with a network of parallel channels that support catalysts. It involves deploying and using chemical kinetic models to understand and optimize how chemical reactions happen within these reactors, which are widely used in industries like petrochemicals and automotive catalytic converters. And how it works. The first one is monolith catalyst. A solid structure or monolith is used as a support for a catalyst. This support is engineered with a high surface area network of channels. The next one is kinetic model. A mathematical model is developed based on experimental data to describe the reaction rate as a function of factors like temperature, pressure, and reactant concentrations. The next one is computational modeling. Software such as Computational Fluid Dynamics or CFD is used to create three-dimensional model of the reactor. This allows engineers to simulate and study the combined effects of fluid flow, heat transfer, and chemical kinetics within the reactor's integrate channel geometry. The next one is optimization. The kinetic models and simulations are used to optimize the reactor design for better performance, such as maximizing the desired product yield or minimizing unwanted byproducts like ammonium in nitrate reduction. And what are the key applications? The first one is exhaust gas after treatment used in catalytic converters for a vehicle to convert pollutants into less harmful gases. The next application is chemical synthesis, employed in the fine chemical industry for processes like hydrogenation reactions. The next one is environmental remediation, investigated for applications like removing nitrates from water. Monolithic kinetics refers to either a kinetic analysis of a monolithic structure or the kinetic performance of a monolithic material or device. A monolithic is a single solid structure, and kinetic relates to the study of motion of or rates of change. Therefore, the phase can be found in contexts like polymerization kinetics of monolithic columns. For chromatography, the kinetics of reaction in monolithic catalysts, or the kinetic performance of monolithic robotic field. And what are the examples of monolithic kinetic? In chromatography, analyzing the kinetic performance of a monolithic column, which is a single rod of material used for separations, is more efficient and faster than packed columns, especially at high flow rates. Research investigates the kinetics of mass transfer within these columns to optimize separation. The next one is in chemistry. The kinetic parameters of a monolith's polymerization process can be determined to optimize its structure for a desired outcome. The kinetics of reactions on monolithic catalysts, like those used in catalytic converters, are used and also studied, especially for reactions like NOx or oxide nitride reduction or hydrocarbon oxidation. And what is their application in robotics and electronics? The term can describe the kinetic performance of monolithic robotic actuators which are integrated into a single flexible film. This process is used to create kinetic electronics that can be integrated into electronic devices or medical instruments. The next application is in material science. The phase or phrase can refer to a monolithic kinetic parameter such as a material made from multi-walled carbon nanotubes immobilized on cellulose, which can be used for applications like gas storage. In summary, monolithic kinetic describes the study of how a single solid object or material behaves over time, whether it's about its assembly or polymerization kinetics or its function, which is kinetic performance. Monolithic and effective kinetic promoter formed by immobilized MWCNT on cellulose for efficient hydrate-based gas storage. Hydrate provides a promising alternative for natural gas storage and transportation through its formation process using only structured water molecules, characterized by mild storage conditions, low energy consumption, and high safety. However, the sluggish hydrate formation kinetics and limited water to hydrate conversion ratio hinder the practical application of hydrate based technologies. The approach of introducing selected solids into the reaction system for boosting hydrate formation via heterogeneous nucleation has been extensively investigated. Nanomaterials are confirmed kinetic promotes for gas hydrate formation with high efficiency, while issues such as flocculation, aggregation, and resultant performance degradation are inevitable hinder the hydrate-based gas storage. Herein we present a strategy in which multi-walled carbon nanotubes or MWCNTs are immobilized onto cellulose to form a monolithic and recyclable and scalable kinetic motor for efficient hydrate-based gas storage. The reactive interface with tunable wettability can facilitate the rapid nucleation and continuous hydrate growth, leading to high gas storage capacities of 138.6 and an extremely short induction time of 3.3 minutes under low driving force is equal to 5 megapascal, and the temperature is about zero point 0.2 degrees of centigrade in the static model. Furthermore, elegant control of the surface functional groups of the as made samples through pyrolysis and plasma treating further regulated the kinetics of CH4 hydrate formation by turning the content of surface oxygen containing functional groups such as CO and NO. Based as made samples also present promoting effects on CO2 hydrate formation, demonstrating excellent potential for practical applications. This work is helpful for our understanding of the mechanism of controlling gas hydrate formation and the design of novel and effective motors. And what about monolithic synthetic routes functionalization and innovative analysis applications? Monolithic materials stand out in separation science because of their tunable properties, easy preparation, high permeability, and readily available surface chemistries. The number of analytical applications of monolithic has increased in recent decades, including innovations in sample preparation, chromatography, and more recently in flow analysis. This review converts these innovative applications beyond their conventional exploitation in liquid phase separations. New configuration for sample preparation exploiting monolithics as extraction materials, as well as the recent approach for the synthesis and the functionalization of inorganic, organic, and hybrid organic inorganic monolithics material are also discussed. A monolith is defined as a single piece of porous material that entirely fills its recipients usually prepared by in reactions. These hierarchically structured materials have been widely applied in separation science, sample preparation, and microfluids since their introduction in the field of chromatography in the 1990s. Monoliths have emerged as alternative to particulate packing materials, mainly because the continuous bed allows percolation of the mobile phase through it at high linear velocities without excessive back pressure. General aspects and specific applications of monolithic phases have been reviewed. According to their chemical composition, monoliths are classified as organic polymers, inorganic polymers generally based on silica, and hybrid organic inorganic materials which combine features from the first two groups. These classes are differentiated by their morphology and physicochemical properties. Generally, monoliths are relatively easy to synthesize even with controlled pore size distribution, and they may be further functionalized aiming at a specific application. Separation by organic polymeric monoliths can be carried out over a wide pH range and are compatible with a variety of mobile phase compositions. However, these monoliths suffer swelling in some solvents, leading to an increase in back pressure during the separation process. In the past, because of the low surface area, organic polymeric monoliths were more suitable for separation of large molecules. Recently, efforts have been made to overcome this hindrance, and several applications for separation of small molecules have been presented. Swelling is not observed in silica monoliths, but they often show radial shrinkage, which reduces the chromatographic efficiency. Silica-based monoliths are restricted to separation in pH between 2 and 8 due to their dissolution and the breaking of the linkage to chemical modifiers. Because of their bimodal pore size distribution, with large micrometer sized true pores or macropores and nanometer sized diffusive pores or mesopores, as well as the high surface area, for example 200 to 300 gm2. Silica monoliths are suitable for separation of both small and macromolecules. Hybrid monoliths, whose structure shows organic and inorganic moieties, arose as alternatives material because of the easy preparation, applicability of high pH, and good mechanical stability. Moreover, common drawbacks such as solvent swelling for porous polymers and tedious functionalization for silica phase are avoided, the latter because of the addition of functionalized monomers during the synthesis. The unique properties of monoliths, such as the diversity of surface chemistries and their tolerance to relatively high flow rates, thus yielding fast chromatographic separations at acceptable back pressure, make them superior in some applications. Traditionally, monoliths are employed in liquid phase separations, mainly liquid chromatography or LC, and related miniaturized techniques such as capillary liquid chromatography or CLC and electrochromatography or CEC. More recently, monoliths have been applied in other miniaturized systems in which the reduced dimensions of columns minimize both shrinkage and swelling, beyond facilitating in the modeling of the stationary phase within the capillary columns. For samples preparation, monolith materials have been used in several configurations such as columns, plates, pipette tips, and coating materials. This review describes innovative analytical applications of monoliths other than traditional liquid phase separations and sample preparation formats, which we highlighted in previous simulations. Novel devices for sample preparation and innovative chromatographic approaches such as application of monoliths in gas chromatography or GC and flow analysis are critically discussed. Furthermore, synthesis routes and functionalization approaches for obtaining more selective materials are also highlighted. And the general aspects. Synthesis of Monoliths is usually carried out by agglomeration of molecular subunits via cluster formation mechanism using unreactive progens to create size control domains where mass transfer occurs as well as large pores to assure the solution flow through the bed. The process involves formation and growth of nuclei which will interact continuously in the mold to produce the monolith structure. And what is about analytical applications? Replacement of porous particles packed in columns by monolithic sorbents has increased in separation sciences and sample preparation. Because of the intrinsic advantages, monoliths have been mostly applied for liquid phase chromatography such as HPLC and CLC and CEC. Innovative applications including microfluidic devices, GC, and flow based techniques have been demonstrated, and advantages of monolithic materials as sorptive phase in new devices for analytic extraction have also been demonstrated. The trends and perspectives. Monolithic materials offer some unique structural properties compared to the traditional chromatography stationary phases based on pores and particles, as the monolithic structure is derived from reagent selection and conditions of synthesis, it is possible to design its characteristics to achieve better performance. Usually, the incorporation of nanostructures increases the surface area of organic polymer monolithic materials, providing better chromatographic efficiency. These suites of examples illustrate the modeling of selective NO reduction that happens as flue gas passes through the channels of monolithic reactors in the exhaust system of a motor vehicles. The simulations are aimed at finding the optimal dosing of NH3, the reactant that serves as reducing agent in the process. Three different analyses are performed. The first one is kinetic analysis. The example takes a closer look at the selective reduction in a single channel of the monolithic reactor. The reaction kinetics is analyzed with the reaction engineering interface using the plug flow reactor type. Detailed process modeling is the next one. The example utilizes the optimal dosing of NH3 as found in the above example as a starting point. This model is set up in the three-dimensional and can thereby reveal the full space dependency of the problem with even better tuning of dosing level. And the next one and third one is thermal stress modeling. The model studies thermal gradients in the monolithic unit caused by heat released from the chemical reactions. The structural mechanics module together with the three-dimensional model above is used for these investigations. This example looks at the reduction of harmful nitrogen oxides or NOx, either NO and NO2 into nitrogen in an exhaust gas after treatment system of a heavy duty diesel truck. The nitrogen oxides are reduced by ammonia that is injected upstream of the after treatment system consisting of catalytic monolithic reactor. The reactors has two catalyst beds with two different catalysts. The upstream bed is a selective catalyst reduction or SCR bed with the purpose of selectively convert NOx to nitrogen. The second bed is an ammonia slip catalyst or ASC. This bed should convert the remaining ammonia to nitrogen. The dosing rate of ammonia has the direct influence on the conversion of NOx. Too low dosing rate leads to exhaust of unconverted nitrogen oxides, while too much ammonia may give ammonia slip or even NOx emission, since a side reaction in the ammonia slip bed is formation of NOx from ammonia. Since the engine load affects the exhaust gas temperature, the volumetric flow rates of exhaust gas, as well as the concentration of former nitrogen oxide, the dosing needs to be dynamically adjusted. This tutorial aimed to getting a primarily understanding of the chemical kinetic in the dual bed reactor. This is achieved by solving the model with the plug-flow ideal reactor type in the reaction engineering interface. The influence of the temperature, volumetric flow rate, and ammonia to NOx ratio is investigated. Model definition, chemical reactions. In this simulation model, a simplified reaction setup is used with 6 reactions in the first bed and 4 reactions in the second bed. In the selective catalytic reduction bed, there are three desired CR reactions that take place. These are the so-called standard SCR reaction, except for the homogeneous gas phase equilibrium reaction NO4. All reactions are heterogeneous catalytic reactions with reaction rates that depend on surface coverage. The surface coverage of ammonia can be related to the fluid phase concentration by assuming that ammonia desorption and absorption are in the equilibrium, with a Langmuir-Hinshelwood mechanism based on this assumption. Global rate expressions can be derived. The competing chemical reactions raise the issue of optimal dosing of NH3 to handle the reduction process in the first bed. Stereochemistry suggests a 1-to-1 ratio of NH3 to NO as a lower limit for the standard SCR reaction. Due to the undesired oxidation of ammonia, it is likely that a stoichiometric excess of NH3 is necessary. The excess ammonia will be converted in the second ammonia slip catalyst bed. The NOx forming side reaction in the second bed motivates as low ammonia injection as possible. This is also important for economic and pressure drop reasons. Single channel model to find the lowest level of NH3 required to reduce the NOx present in the exhaust gas. A reactor model accounting for changing reactants, compositions, and system temperature is needed. From a mass transfer point of view, channels of the reactor monolith can be considered to be uncoupled to one another. Therefore, it is reasonable to perform simulations where a single reactive channel modeled by non-isothermal flow equations represents the monolith reactors. These equations are available within the plug flow reactor type in the reaction engineering interface. The next one is monoliths. The name monoliths stems from the Greek mono and lithos, single and stone. In catalyst reaction engineering, a monolith is defined as a single block of catalyst containing material through which reactants and products are transported by convection. It has such macroscopic dimensions that one or a few monoliths can completely fill the catalyst reactor space. In separation technology and in flow chemistry, reactor filling rods with well-defined macro and mesoporosity are used. And the next one is reactors and reactor configuration. Monoliths are flexible to operate They are well suited to semi-batch, batch, continuous, and transient processing. Catalyst conversion can be combined between or separation. Catalytic reactions can be combined, and heat integration is possible. Monolith reactors offer high precision combined with a high efficiency compared to most other structural reactors. They are cost effective and they can be obtained in a large variety of materials, ceramics, metals, or polymers or carbon. And here you can see that it has been listed major commercial and potential attractive applications. Monoliths are the state-of-the-art reactors in many practical applications in environmental catalysts because of the low pressure drops at higher flow rates, the dust tolerance, and etc. And what are the recommended subjects? It's the application of a monolith reactor, for example, diesel particulate filters or DPF, catalytic incineration, catalyst, support for chemical process, and vehicle emission control. And what about the first application? A diesel particulate filter or DPF is a device designed to remove diesel particulate matter or soot from the exhaust gas of a diesel engine. And what is the mode of action? While flue diesel particulate filters usually remove 85% or more of the soot and under certain conditions can attain soot removal efficiencies approaching 100%. Some filters are single use intended for disposal and replacement once full of accumulated ash. Others are designed to burn off the accumulated particulate either passively through the use of a catalyst or by active means such as a fuel burner which heats the filter to suit combustion temperatures. This is accomplished by engine programming to run when the filter is full in a manner that elevates exhaust temperature in conjunction with an external fuel injector in the exhaust stream that injects fuel to react with a catalyst element to burn off accumulated soot in the DPF filter or through other methods. This is known as filter regeneration, and cleaning is also required as part of periodic maintenance, and it must be done carefully to avoid damping the filter. Failure of fuel injectors or turbocharge resulting in contamination of the filter with raw diesel or engine oil can also necessitate cleaning. The regeneration process occurs at route speed or higher than can generally be attained on city streets. Vehicles driven exclusively at low speed in urban traffic can require periodic trips at higher speed to clean out the DPF. If the driver ignores the warning light and waits too long to operate the vehicle above 60 kilometers per hour, the DPF may not regenerate properly, and continued operation past the point may spoil the DPF completely, so it must be replaced. Some newer diesel engines, namely those installed in combination vehicles, can also perform what is called a parked regeneration, where the engine increases RPM to around 1400 while parked to increase the temperature of the exhaust. Diesel engines produce a variety of particles during the combustion of the fuel-air mix due to the incomplete combustion. The compositions of the particles varies widely depending upon engine type, age, and the emissions specification that the engine was designed to meet. Two-stroke diesel engines produce more particulate per unit of power than do four-stroke diesel engines, as they burn the fuel air mix less completely. Diesel particulate matter resulting from the incomplete combustion of this fuel produces black carbon particles. These particles include tiny nanoparticles smaller than 1 micrometer or 1 micron. Soot and other particles from the diesel engine worsen the particulate matter pollution in the air and are harmful to health. New particulate filters can capture from the 30% to greater than 95% of the harmful soot. With an optimal diesel particulate filter or DPF, soot emissions may be decreased to 0.001 gram per kilometer or less. The quality of the fuel also influences the formation of these particles. For example, a high sulfur content diesel produces more particles. Lower sulfur fuel produces fewer particles and allows use of particulate filters. The injection pressure of these also influences the formation of fine particles. And what is about the history? Diesel particulate filtering was first considered in 1970 due to concerns regarding the impact of inhaled particulates. Particulate filters have been in use on non-road machines since 1980 and in automobiles since 1985. Historically, medium and heavy-duty diesel engine emissions were not regulated until 1987, when the first California heavy truck rule was introduced, capping particulate emission at zero point 0.6 g per bhp hour. Since then, progressively tighter standards have been introduced for light and heavy-duty road-going diesel-powered vehicles and for off-road diesel engines. Similar regulations have also been adopted by the European Union and some individual European countries, most Asian countries, and the rest of North and South America. Whilst few jurisdictions have explicitly made filters mandatory, the increasing stringent emissions regulates that engine manufacturers must mean that eventually all on-the-road diesel engines will be filled and fitted with them. In the European Union, filters are expected to be necessary to meet the Euro and the heaviest truck engine emissions regulations currently under discussion and planned for the 2012 and 2013 timeframe. In 2000, in an anticipation of the future Euro 5 regulations, PSA Peugeot Citroën became the first company to make filters a standard to passenger cars. As of the December 2008, the California Air Resources Board or CRB established the 2008 California statewide truck and bus rule, which with variants according to vehicle types, size and usage, requires that on-road diesel heavy trucks and buses in California be retrofitted, repowered and/or replaced to reduce particulate matter or PM emissions by at least 85%. Retrofitting the engine with CARB-approved diesel particulate filter is one way to fulfill this requirement. In 2009, the American Recovery and Reinvestment Act provided funding to assist owners in the offsetting the cost of diesel retrofits for their vehicles. And you can see these reactors for monolith and the vessel or bed here, and the generator and condenser and turbine. And here you can see that I have used a reaction as a physical measure, and you can see the formula here. And as it is obvious, you can see the all of NO or oxide nitride that is here, H2O, that's water, and nitrogen and other sort of species, and also the equilibrium and equation. And Last thing is the result, that is SCR temperature operating, SCR temperature operating window, and temperature operating window. Thank you so much for watching my tutorial video until the end. And also you can download this video from my github.com/masterscript.